Okay, we're on. All right, first of all, homework 4 is due today. Obviously, a lot of people haven't handed it in, and I can see there's a lot of random numbers here. Maybe that's appropriate for the course. But I'll take them late. If you hand it in late before I go over it in class, which will be next time, that's much better than if you hand it in after I go over it in class. And depending on how late it is, the number of points I'll take off will depend on that, but not much. In other words, I won't take off very much for being late. I ought to take off a little bit because it's not fair to the people who got it in on time, but the important thing is to do it and do it as well as you can rather than have to worry about artificial deadlines. So hand it in as soon as you can if you haven't already done it. Now, any questions about that? I'll do this in class probably on Thursday. Now, as far as our schedule is concerned, I was talking about the central limit theorem, and I said I was going to assign homework 5. But we're getting jammed up on time here because we have this week and then next Tuesday, and then next Thursday, is Thanksgiving, so we miss that. And then right after that, we have the last week of classes. So I don't have time to do these things, to give a homework, in which there's at least a week between the assignment and when it's due, and be able to discuss it. So what I want to do is I'm going to skip homework 5 for the moment, and I'm going to do homework 6, which I'm going to start talking about today, and then we'll get back to homework 5 at the end if we have time. And it may be that I won't have time to assign it, in which case I'll just do it. Because I always do it in class, and I tell you if you run it, you will find out that the theory and the simulation agree. And by this time, although it's always nice to do that, by this time you ought to believe it. So in that sense, it's really not necessary to actually run it because you know what's going to happen. So we'll worry. So we'll worry about homework 5 later, and I want to go to homework 6 because that's really, to some extent, it's a high point of the course because it gets to the point now where you're going to actually look at an application of this stuff to a real problem. All right, so what I'm going to do is I'm going to discuss homework 6 today, and you should go to the website and print it out and have it with you on Thursday to ask any questions. Actually, it's very easy. It's easy to do, but it's sophisticated to understand. So I'm going to try and explain it, but when you actually do it, you'll see it doesn't take very long. And then that'll be due on the following Tuesday. So, let's see. Homework 6 will be due a week from today. And then I'll be able to hand it back. So it'll be due before Thanksgiving, and I'll hand it back after Thanksgiving. So that means you don't have anything to do over Thanksgiving. You can relax. All right, so any questions before we start? All right, now, homework 6 is about queuing theory. It's called the MG1Q. So let me explain what this is about. First of all, the subject in general says that you've got this system and there are random demands. So you're designing a system of some sort, and the system has fixed resources, but the demands are random. And there are lots of applications of this. And in our particular context, what I want to look at, just to be concrete, is to look at the case in which we have messages in the Internet. So we can imagine that we have a node or a communications channel in the Internet, and messages arrive at random to the channel, and then they are transmitted to another place in the Internet. And so you've got all of these random messages bopping around all over the place. And the question is, how do you analyze and design such a thing? So it's part of this basic big idea where you've got random demands and some system with fixed resources, and you want to know what the behavior of the system is as a function of the random demands. So there's really two pieces to this. There's the randomness in the demand, and then there's the physical configuration of the system. So we start off with the simplest version. This is sort of like a building block. And in fact, it has a name, which is called MG1. I'll explain that later, but it's only a name. And the idea is this. Here is your server. So this will be, in general, it's called a server. And in our case, to be specific, we'll call that a channel. And then you have messages which arrive, or customers. So a customer arrives, and if the server is available, then he holds the server for a length of time, which is random, and then at the end of that time he goes away. And if another customer arrives when the server is not available, when the server is busy, then that customer waits in a queue. And another one might arrive, and then he waits in a queue, and so forth. So you have these arrivals occurring at random, and in fact you can draw a picture like this. Let me erase this guy right here. So here's what's happening. Here's time, and imagine that you have two urns. So one urn, I have tickets which I'll call inter-arrival times, and the other urn, I have tickets, I'll call those service times. So IA stands for inter-arrival times, X stands for service times. And in general, these are random. So imagine the picture looks like this. A customer, or message in our case, arrives, and it's at a random time, and I get that when I simulate, which I'm going to explain shortly, by drawing from this urn here. So I reach into the urn, I pull out a value, and that tells me when the next arrival is going to occur. And then I reach into this urn, I pull out a value, and that tells me the bandwidth requirement, or the service requirement, or the service time of the customer. So a message arrives, and he needs this much time from the channel. And during this time, the channel is not available to anybody else, and when this time ends, then a new arrival can use the channel. So imagine that you have generated these things. Either you've observed them through data, you've observed this, or you generate them by picking numbers out of these urns. So here's an arrival, there's the next arrival, here's his service requirement, there's the next arrival, there's his service requirement, and so on. Now, if you knew exactly when the arrival times were, and you knew exactly how much service each one requires, then if you had the patience, you could trace through, and you could figure out for each customer how long he had to wait, and then taking all that data, you could figure out the average waiting time and the fraction of customers or messages that had to wait more than 10 seconds or whatever you wanted. But first of all, it's very boring. And second of all, it doesn't really mean that much because it would only be true for this specific case. So what you want to do is you want to have a model that will specify the distributions of these values and then quickly run it through this configuration, and then it'll produce some answers, which will tell you things like how busy is the server, and how long is the queue, and how likely is it that the queue will exceed a certain length so that messages overflow the buffer, or things of that sort. So what we're going to do is we're going to look at that, and this is in fact part of a theory, or there's a whole theory about this. This right here now, let me see this. These are the customers or arrivals. So customers arrive at random, and they make a request from the server, and if the server is busy, then they wait in a queue. And in our particular example, the customers are messages, and the server is a channel. Now, since the customers wait in a queue, since this is sort of like a building block for this kind of subject, a whole theory has grown up about this. It's called queuing theory. So here's Q, U, E, U, E. So a queue is a waiting line, and the theory is called queuing theory. And you can see that this stuff is obviously difficult, at least at first pass, and it's obviously important. And so this kind of thing is on the boundary now between what engineers know and what they know in terms of a theory that gives them formulas and methods for simulating when the theory does not apply. So this is right on the boundary here between toy problems, like what we've had before up to this point, whose value is just to illustrate the way the theory works, and the actual way that people use this kind of theory. And in fact, if you look at our courses, say in the graduate program in communications, data communications, things like that, you'll see that roughly they divide into two pieces. One piece has to do with the way in which things work. Those are the protocols. So that's the physical description of what's happening, and most of our courses tend to concentrate on that. But the other aspect is the performance of these systems, and the main tool that's used there is queuing theory. So in fact, if you look at some of the textbooks, maybe I can go into that next time, you'll see that. You'll see exactly what I'm talking about. Okay, so we have this queuing theory, and actually, historically, this stuff dates back from the beginning of telecommunications. The telephone was invented, they say, in 1876. Alexander Graham Bell invented the telephone. And in 1878, the first commercial exchange went into operation. And so what it amounted to was a bunch of subscribers and then some channel or a way of connecting the subscribers to each other. And people say that as soon as the third subscriber showed up, that's when queuing theory was born. Because if you have one channel, you can only connect two subscribers at a time. Then as soon as the third subscriber is there, then if he wants to make a call, if the other two guys are talking, the channel is busy and he has to wait. And so as soon as that happened, then engineers, mathematicians started working and trying to solve these kinds of problems. And they didn't really make very much progress until the early 1900s. And then somebody named Erlang, A.K. Erlang, who worked for the Copenhagen Telephone Company, made a breakthrough. And he came up with a method and with formulas that are still used today. And the measure of traffic, in fact, is called the Erlang, is named after him. So that dates from the early 1900s. I think he published his paper, his famous paper, in 1917. And the subject has been under continual development since then. So it's almost 100 years old now. So lots is known. There are lots of papers, lots of books, literally thousands of papers. So it's kind of surprising, probably most of you never heard of this. But if you go to the internet and you go to a search engine and type in queuing or queues or something like that, you'll make thousands of hits. And so you'll see that although at the undergraduate level this doesn't usually make an impression, and most of the world can live their whole lives without any knowledge that this stuff exists, it's out there, and it underlies the design of almost all shared technological systems. That is, systems like the internet, like telephone systems, like all kinds of networks, of transportation networks, networks that are used for the analysis of manufacturing. For example, in a manufacturing system, you've got these materials that go from place to place and work is done on them, and each one can be viewed as a random arrival, and the amount of work required is sort of random, and you've got this production line, and you have to worry about bottlenecks, and you want to make sure that what goes in comes out in reasonable time as cheaply and as quickly as possible. And so queuing theory is one of the major tools that's used by industrial engineers to design these kinds of systems. So we're looking at the simplest major building block, which is the single server queue. Okay, so one thing I might refer you to is if you go to my website, which is just okay, let's see, www.cse.fau.edu/squigglebob, then you'll see that a lot of the work that I've done in my career has been in this subject in queuing theory, and there's a bunch of papers listed here and a description of what this subject is about. And in particular, if you look at the list of what's called selected publications, there's a paper called Queuing Theory, and it's an encyclopedia article. So it's from the Encyclopedia of Computer Science. And you can download that, or you don't have to download it, you can just read it. And at least at the beginning, don't have to go too far, it'll explain exactly what I'm saying here. Also, I might add that if you look at this and you get kind of interested, two things. First of all, I'm going to try and convince you that this subject is really very useful and very interesting. And second of all, that don't be scared, it looks a lot harder than it really is. And part of the reason for that is that this lecture is actually an advertisement, because I teach a course called Queuing Theory. It'll be given in the spring. It's a graduate course, and it's part of the group of courses that in our graduate program we call theory. And one course from that group is required for all the master's students. Not necessarily that one, but that's one of them that satisfies the requirement. But also there's an undergraduate course called Introduction to Queuing Theory, and that's an undergraduate elective which satisfies the math requirement. But we haven't given it very often recently because of the economics of the situation. As class sizes get bigger and faculty gets smaller, and we're under more pressure to be more economical and operate more like a business and less like a university, we can't teach these courses unless we have enough people signing up. And since it's only an elective, and since it's scary anyhow, a lot of people don't take it. So what I've decided to do this time is I'm going to offer the graduate course and the undergraduate course together. Actually, it's a feeds course, and graduate students and undergraduate students will sit in the same class and see the same lectures, but the assignments will be different or graded differently, so it'll be easier for the undergraduates. So if you're interested, which I hope you will be after we discuss this and you do this homework, then these are the courses. So MAP 6264, that's Queuing Theory. That's the graduate course. And MAP 4260, that's Intro to QT. That's the undergraduate course. So if you're an undergraduate, you can sign up for this one, and there's a lot of overlap between the two. And in fact, for you as students, it'll be easier for you for much of it than it will be for the graduate students, because this course is a natural continuation of stochastic models. But the graduate students haven't had stochastic models for the most part because they come from all over. So although they're required to have had some course in probability, it's surely not exactly the same as the course you have. So a lot of time is spent reviewing, talking about the inverse transform method and things like that. And so you'll be ahead of the game at the beginning. And the general structure of the course is just like this course, which is that in class I do some theory and derive some formulas, and then homework assignments consist of writing simulations and running simulations that produce the values that the theoretical models predict, and then you compare the two, just like in this class. And in fact, that's what this first homework is about, so you'll get the idea. Okay, so that's part of the advertisement. So let me erase this now. So there's two pieces to this. What I need to do is I need to generate the inter-arrival times and the service times. So I get, in effect, this data, this information, and I'm going to take this and I'm going to run it through this template and simulate it, and then compare the simulation results with the theoretical results. Now the theory, first let me explain why this theory ought to be so difficult that it's impossible. And then of course it's not, it's really very easy, but let's start with that. Okay, what's going on here? Take the viewpoint of a customer. A customer arrives, and one possibility is he arrives and the server's available, and he just takes the server, and then he stays there for a random length of time. But the typical case is a customer arrives and he finds a queue in front of him. So here's the customer arriving, and he finds this queue, and you want to be able to analyze this, and you want to know things like, what is the average time that a customer spends waiting in the queue before he begins service? So imagine that you're this customer, you arrive, and you say, well, how long am I going to wait? And you say, well, the time I'm going to wait is going to be the sum of the service times, the service requirements, or the bandwidth requirement of every message that's on the queue in front of me, plus the partial service time of the customer or message that was in service who I interrupted when I arrived. So that means that if I wanted to do this in a straightforward, direct way, The waiting time of the new customer would be the sum or the convolution of the density function of each of the service time requirements of the customers in the queue, which of course could be any number of convolutions, plus the convolution with a partial service time. And furthermore, not only is that bad enough, but the number of terms in the convolution is itself a random variable. Because when a message arrives, how does it know how many messages are in front of it? Well, it doesn't. We can derive the distribution of that. In fact, we're going to do that. But generally speaking, if I look at this as a direct question and try and handle it without any insight or intelligence, it's going to be extremely difficult. So you would expect that you wouldn't be able to get much. But what I'm going to show you is that there are formulas that describe the behavior of this, which are unbelievably simple. And then we'll check those formulas against the simulation, which then consists of two parts. It consists of generating these guys, these two random variables, the arrival times and the service times. And you already know how to do that, just the inverse transform method. And in the homework problem, I'm just going to ask you to do this for 3 different service time distributions, which are 3 you've already seen: exponential, constant, and uniform. So there's nothing new in terms of writing the inverse transform method. And then you run those values through this template. That's the physical configuration. So you have to represent this logically in the computer. Now, this looks like it might be difficult at first glance because you're going to need some kind of record keeping, because obviously, well, sort of obviously, actually not obviously, because I don't need this, but a naive view is, well, if I had all the arrival times and all the service times, it would be theoretically simple, but actually complicated to trace through the whole picture and know exactly how long each individual customer or message waits. So I'm going to show how you simulate this, and believe it or not, essentially the code that describes this complicated looking system consists of essentially one instruction. And it's common, as you'll see, especially if you take the queuing theory course, that once you get the hang of it, these simulations are very simple, and the whole thing is very powerful. So I'll try and convince you of that. So the thing I got to keep saying is, A, this is useful, because there's a whole lot of practical-minded people out there. They want to know how I'm going to earn a living. So I got to say it's useful. You can actually earn a living doing it. I earned a living doing it. Although it wasn't that great, that's why I became a professor. But that's because being a professor is a lot more fun. Because it's a lot more fun to do the theoretical stuff than to actually worry about the actual numbers. Because then if it doesn't work, people complain, and who wants that? But the point is, it is practical. The other point, which I'll try and illustrate, is that it's actually very interesting. And one of the strange things here is that how can a grown man spend his whole life worrying about people waiting in line? I mean, it's the stupidest thing you could think of. But nevertheless, as I say, there are thousands of papers and there are thousands of people throughout the world who do this on a professional basis. Okay, so let me show you how to write the simulation, which I'm writing for you, but I'm explaining where it comes from because it looked rather mysterious at first. So let's take a customer who arrives, and let's call T sub n the arrival time of the nth customer. So where T sub n comes from is I'm pulling the times out of this urn, and the times, this might be T1, T2, T3, and so forth. And the way I get those is I pull the inter-arrival times out. So T1 is the first value that comes out of the urn. And T2 is the first value plus the second value. So as I add up the inter-arrival times, I get the actual times that the customers arrive. So this is the arrival time of the nth customer. Now, when this customer arrives, in general, he's going to wait. So let's say that he waits that long. I'm going to call that value W sub n, or waiting time of the nth customer. Now, this could be 0 because if this customer arrives when the server is idle, then he gets served immediately and his waiting time is 0. But typically he arrives when the server is busy and then he has to wait. And after he waits, then he enters service, and the length of time he spends in the server is xn, That's the value I draw from here. So that's the service requirement of the end customer. And then when he gets that service and it's finished, he leaves. So this represents a single customer. Now, what about the next customer? There are two possibilities. The next arrival could occur here after this arrow, or it could occur before the arrow. Now, suppose it occurs after the arrow. And by the way, the assumption that I'm making here, I haven't stated it, I'll state it now, is that service is FIFO. First in, first out. In other words, you get served in the order in which you arrive, your ordinary standard queue. Okay, so if we have FIFO service, then if customer number N has already finished before customer number N plus 1 arrives, then customer number N plus 1 will find the server idle, and so his waiting time will be 0. So that's the easy case. So in this case, Wn plus 1 equals 0. Okay, so what about the other case? Suppose that T sub n plus 1 occurs, of course it has to occur after T sub n, but suppose it occurs before the time that the customer who arrived here leaves. So I'll just make it arbitrary right there. So suppose that's T sub n plus 1. Okay, now if that's the case, how long does this customer wait? And you can see from the diagram that the answer is that the waiting time for customer number N plus 1 is that distance right here. This is when he arrives. This is when the customer in front of him leaves. So the difference between those is how long he waits. So this suggests a recursive argument because I can relate the waiting time of customer N plus 1 in terms of the waiting time of customer N. And when I do that, I get a single statement, basically that translates to a single instruction, and the whole thing is done. Okay? So let me write that down. Let's see, I think I'll write it, where should I write it? Okay, I'm going to write it up here. So you can see this diagram. And the statement is this. The waiting time of customer N plus 1, that's this, is equal to the waiting time of the customer in front of him plus the service time of the customer in front of him, that plus that, minus the time between their arrivals, which is the inter-arrival time between customers N plus 1 and N. So that's a recursive definition. Customer number 11 waits the length of time the customer number 10 does, plus the amount of time the customer number 10 spends in service, minus the time between them. Okay, so in the case in which T sub n plus 1 occurs before this guy, then this arithmetic will say how long customer number n plus 1 waits. And in the case in which the customer number n plus 1 arrives after that guy leaves, then he waits 0. So if I take this equation and I plug in the actual values, if that plus that minus that turns out to be negative, that's what happens in this case. If this is bigger than this plus that, then this thing is negative. So the way I define this mathematically is I put parentheses around here and I write a plus sign. So what this notation means is that if I want to calculate the waiting time of this customer, I calculate whatever's in here. Remember now, these are random variables, but the simulation is going to do this for us. I calculate whatever this is. If this value turns out to be negative, then I replace it by 0. That's what the plus means. And if the value is not negative, then I take whatever value it is. Okay? All right, so this is the simulation part. This is the code. I'm going to write this code, and it's already done for you in the homework, which I wish I had told you beforehand so you would have it in front of you, but it's not a big deal. I have it in front of me, so I guess that's what counts. Okay, so to summarize now, what we have is we're going to write a simulation which is going to express this physical configuration, which is just a single server queue. and then we're going to drive that configuration by submitting to it random arrival times and random service times, and run those things through the template and see what it produces. And the stochastic part is simply the part that we've had in this course so far, which is we put some random variable distributions in here, some population, and we use the inverse transform method for the computer to generate them. And then it sends it to this template in which the values are represented recursively by this. And what this says, from this diagram, it says that the waiting time of any customer is equal to the waiting time of the customer in front of him plus the service requirement of the customer in front of him minus the time between their arrivals. And if that's negative, that means that this customer waited 0, and so this plus sign indicates calculate this, and if it's negative, replace it by 0. And if it's not negative, then whatever it is, that's the answer. And then the simulation simply does this for thousands of samples drawn from here and here, and simply calculates this for every different x and I, and computes an n, and then uses that to compute the next one, and simply computes all of these values. Okay, so that's the theory of the simulation, and then when we get done with that, I'll explain what it is we want to measure and show how the theory of probability gives us formulas that allow us to calculate these things. And these formulas have two important pieces to them. Well, three. One is they're simple, or at least for the cases we can get they're simple. So maybe there's 4 important pieces. In fact, the more I think of it, the more important things I think about. The formulas are important because, at least what we're going to see, is they're simple. They, of course, give correct numbers. But in addition, not only do they give numbers, but they give insight. So when you look at the formula, as you'll see, you can understand why the results turn out to be what they are. And it'll have to do with important concepts in the course, like mean and variance. Okay, so let's go through the code here. So any questions so far? Should be simple, right? Yes?
Sometimes you call a phone company or something like this, they'll tell you a waiting time. So that would be an applicable formula. It says sometimes you call
Yes.
a company and then they'll tell you your waiting time is approximately...
Exactly. In fact, those are called call centers. And what happens when you call one of these call centers where they have agents that answer the phone, if an agent is available, then you'll get an agent. But often the agent isn't available, and then they'll give you a message saying how important your business is, and please wait, and they'll play some stupid music and ask you not to hang up. Well, actually, what's happening there is you're waiting in a queue. And of course, the call center, they don't know when people are going to make requests for service, when they're going to call up. They don't know how long the request is going to take to be handled. And it costs them money to provide these agents because they pay the agents. Now, if they have too many agents, you get good service, but the expense of running the call center is very high. If the number of agents is too small, they save money in the salary of the agents, but they lose customers because people get annoyed and hang up, or they overflow the buffers that are provided to hold them. And so exactly these formulas are used to determine what the trade-off is between the number of agents to provide, the number of servers. In our case, we're going to make this number of servers 1. But in general, that's one of the questions. How many servers should I provide so that the service I give is what I want? And the constant trade-off is that for any particular configuration, you know what it costs to provide that service. And this theory tells you what the performance would be, and then you can decide whether you want to spend that money or how you want to allocate the money. So yeah, it's a perfect example. Okay, so here's my code. So this code is in BASIC, of course, but you can change it to anything you want. And so what I'm going to do here is I'm going to run 100,000 customers through this template. So it's going to be 4 I equals 1 to 100,000. Now you can run any number you want. You could run 1,000,000, of course it'll take it 10 times as long, but these things run so fast that that's no big deal. if you run less, then, well, the less you run, the smaller the sample size, the less reliable the answers are. And I've done this before, and 100,000 seems to work perfectly, so that's my recommendation. Okay, statement number 110. Now, the first thing I'm going to do is I'm going to select from this urn and find out when the arrival time of the next customer is. So IA equals. So now I have to write an instruction that corresponds to sampling from the inter-arrival time population. So we'll get back to that in a moment, but that's the inverse transform method. That's the stochastic part of the course. Except for sampling from these two urns, there's no probability in the simulation. Remember, the simulation is simply programming, simply logic. Okay, so this says, okay, sample from this urn and draw the ticket, and that tells me when the arrival is. Then statement number 120 is T equals T plus IA. Now, T is going to correspond to the clock here. This is the actual absolute time. Here I've had a subscript, but in the program I don't have a subscript. So this says that the current time is whatever it was before plus the inter-arrival time that I just drew. So, in other words, I have this time scale here, and here's my value T. This is the arrival time of the customer, the last customer, and now I'm going to draw from this urn, and I'm going to find the inter-arrival time. I'm going to add that to the old clock time, and that'll give me my new T. So the clock moves forward in increments, which are the times between the arrivals of the messages. So this is my absolute clock time. Okay, now comes the key instruction, right over here, which says that now the waiting time of the customer who just arrived is going to be equal to the waiting time of the previous customer. So whatever W is the last time I computed it, plus the service time of the previous customer. So that had to have been drawn from this urn previously. Initially, of course, that's 0 and that's 0 the first time through, minus the inter-arrival time. So this is exactly this. The waiting time of the current customer is the waiting time of the previous customer plus the service requirement of the previous customer minus the time between their arrival. But the question is that positive or not? So I calculate this thing, that's the waiting time, and then statement number 140, I say if the W that I just calculated is negative, if I calculated a negative value, that means that the waiting time was 0, so then I set W equal to 0. So these two instructions are this. And the second one, 140, that's just this plus sign here. So this is everything. Statement number 150. Now, for the purposes of this simulation, one of the things I want to calculate is what fraction of the customers have to wait in the queue? What fraction of the messages do not get served immediately? So now I'll say if the W that I just calculated is greater than 0, means the customer had to wait, then I want to count it. Then C equals C plus 1. So eventually what I'm going to do is I'm going to count all the customers who have to wait, divide that by the number of customers. That'll give me the probability that a customer has to wait. Statement number 160. SW is equal to SW plus W. Sum of the waiting times is equal to whatever it is so far plus a new waiting time. So I'm going to accumulate all the waiting times for the purpose of calculating the average waiting time. Because one of the performance measures I'm interested in is, on average, how much time does a customer or a message spend waiting in the queue? So this is going to accumulate all the waiting times. Statement number 170. Now what we've done here is Here I generated the inter-arrival time of a customer. Here I calculated his waiting time in terms of the waiting time and service time of the previous customer. Then here I decide whether or not he had to wait so I can count it. And here I add it up, I accumulate it so I can count the average. So now I know what happened to this customer, but now I have to generate his service time because that's going to affect the waiting time of the customer who comes next. So now we have x equals, so now is the point where I sample from this urn. So I have to fill in the inverse transform method for generating the times between arrivals. I have to use the inverse transform method to generate the required service, the bandwidth of any individual customer. But here and here are the only places where there's any probability theory. The rest of it is just logic, just counting. Statement number 180. For reasons that are going to become clear in a moment, I also want to accumulate the service times. So the sum of the service times is equal to whatever it was before plus ux. Statement number 190 says next I. And then there's one more statement, which is a print statement, which I'll write in a minute. But let me go back over this code and write down exactly what all of these things mean. Okay, so this and this simply say I'm going to run through this loop for 100,000 customers. What I'm going to do is I'm going to generate when a customer arrives by generating his inter-arrival time. So IA is inter-arrival time. Inter-arrival time. Okay, so that's what's going to be generated here. Then this T is the actual clock time. And so the clock time, the total time simulated, is whatever it was up to this point, plus the new inter-arrival time, because I'm going to move the clock over piece by sampling from this urn. So T, this is T, equals, I'll call it clock time. Then this gives me the waiting time. This, of course, is this recursive instruction right here. So W is equal to waiting time. And this instruction is really part of this because all this does is check to see whether or not the waiting time is 0 or not. This thing simply counts how many customers have to wait. SW is the sum of the waiting time because I want to add them up and divide by 100,000 so I can get the average waiting time. So SW is equal to sum of waiting times. X is the service requirement. So it's the amount of time that a customer needs or a message needs in order to be transmitted in this channel. So it's a service time. In our case, it's the bandwidth requirement. And that comes from here. We're going to draw some random variable out of here. So remember, the times between arrivals, or in other words, the arrival process is random, and the service requirements are random. If they weren't, then of course the whole thing would be stupid and simple and worthless. So the whole point is that the input is random. Sx is simply the sum of the service times, as you can see. So it's the cumulative amount of time that the server is busy. Sum of service times. And then this instruction says go back and do this again. And finally, I want to print out my answers. Okay, so this is statement number 200. Print. Okay, now what I want to print here is, first of all, the sum of the service times divided by T. Okay, now why is that? What is that? Well, every time a customer arrives, eventually he gets served. And so if I add up the total, the sum of all of the service times of all of the customers who have arrived, then by the end of the simulation, the value of Sx will be the total time that the server was busy. Now there'll be a little error in there because whenever I stop the simulation, since it's finite, there will always maybe people waiting in the queue, so they won't be counted. But if I'm going to do hundreds of thousands of these, those few different customers that aren't counted aren't going to make any difference. So this adds up the total busy time of the server and divides it by the clock time, which is total time simulated. So this ratio is the fraction of time that the server is busy. Okay, so let's see. Why don't I write this over here? Where can I write it? Sx over t. It's the utilization of the server. So the question is, how busy is the server? Is it busy 10% of the time, 20%, 90%? The busier the server is, the more efficient the system is, in the sense that if you're paying for this, then if he's sitting idle doing nothing, if he's not working, then you're wasting your money. So this represents the fraction of the time during the simulation that the server was actually working. But there's a trade-off, because as you'll see, the more efficient the server is in the sense that it's not sitting idle, the longer the queues are going to be, and the worse the service is going to be for the customers. So this is an accountant's problem. The accountant has to decide whether he wants to give good service, low delays, but have the server be used inefficiently, or whether he wants to be efficient in the use of the server, but thereby induce long delays. So the simulation will show that. So the first thing I'm printing here, that's why I wanted to calculate the sum of the service times, is I want to get the utilization of the server. And there's going to be a formula for this, so you're going to check this result with what the formula produces. Of course, it's going to agree very well. The next thing is C divided by 100,000. Okay, well, what's that? C divided by 100,000. C is the number of customers that waited in the queue. 100,000 is the number of customers that's generated. So this is the fraction of customers who wait in the queue, or it's the probability that a customer has to wait. So this value right here is in fact the probability that the waiting time is greater than 0. Because what I did was, I counted how many waited greater than 0, divided by how many there were. That's the fraction, or the probability, that a customer has to wait in the queue. So one of the questions you want to ask in terms of performance is, as a function of how busy the server is, what's the fraction of customers who have to wait before they get service? That's one of the performance measures. And the third thing I want to print out is SW over 100,000, and that's obvious. SW is the sum of all the waiting times. So if I divide the sum of the waiting times by the number of customers, I get the average waiting time. And that also is one of the main performance measures. So this measures how busy the server is. This measures how many people wait, how likely you are to wait. And this measures how long you wait. And those things are all related somehow. Now the simulation, of course, just gives you numbers. So when you run the simulation for any particular distribution here, any particular distribution here, you're simply going to get numbers. The theory, when theory is applicable, which isn't always the case here as we'll see, the theory then will tell you not only what those numbers are, but it'll give you insight into why those numbers are what they are. So therefore you can gain some intuitive feeling for the way these systems work, and you know what the trade-off is between the provision of the resources and the quality of service that results. Okay, so before I go into this piece and this piece, are there any questions about the logic of the simulation? So I want to press on you two things here about the simulation. If you look at this logic, all of the what looks like the difficult bookkeeping that arises because, remember, all you're doing is running through this configuration all of this data, which represents the arrival times and the service requirements of every customer. So it looks like a complicated thing to do, but it's all done in this single mathematical statement, which is, in fact, this instruction, or these two instructions right here. And the rest of it is just simple-minded. There's really nothing to it. So I just gone through this thing like that, and that's the end of it. So the first thing is, this is a recursive kind of relationship, and I've tried to stress that the probability, maybe in lots of other areas too, you can often pull yourself up by your bootstraps. You don't really have to know what you're doing. If you could simply say what happens to case number n plus 1 in terms of the previous case without really knowing what it is. So this is it's always nice to be able to get something for nothing, and this always appears to me to be getting something for nothing. So it's a recursive kind of argument. And the other thing is that it's so simple, because this looks like it's complicated, but here's all the code, and essentially the code is this, right there. And the rest of it is just counting what actually happened. So now we got to look at this instruction and this instruction. But we didn't need any probability. In other words, the first day of class, if you know how to program, I could have gone through this and said, well, this is some random stuff that comes out of this population, and this is some random stuff that comes out of a population. Actually, it doesn't matter. We could actually have real data in here, just be picking tickets out, and we could run it through here, and this would then mimic the single server queue, and would calculate things like average waiting times, fraction of wait, and fraction of time the server's busy. So, everybody okay on that? Any questions about this? That means clear, right? Okay, so let's go to this and this. So now we get to the stochastic point. So let me erase this. So statement number 110, inter-arrival time equals. So now I have to have something. I got to put something in this urn here, and these numbers on these tickets should somehow or other correspond to reality. So I made the argument earlier that if you wanted to describe a process of events occurring at random, that the best way to do it was to use the exponential distribution as the times between events. If you remember, we made an argument like this. We said, suppose that we have a totally random process. The example I used, besides messages arriving, was a Geiger counter. What we did is we said, okay, what we'll do is we'll simply imagine we divide time up into little intervals, and we'll imagine there's some t here, and then we will, if I call the length of time until I get my first arrival, there it is, IA, then the probability that IA is greater than t, if you remember we took this limit, and it turned out that the answer was e to the minus lambda t, where lambda is equal to the arrival rate. And 1 over lambda was equal to the expected value of the inter-arrival time. When I originally derived it, I called this x because it was just a generic random variable, but now I'm talking specifically about inter-arrival times. So we derived this. This was the so-called Poisson process. And everybody agreed that this was the most reasonable, least presumptive model you could make of events occurring randomly in time. Anything else means that you're going to impose other assumptions, because the assumptions that are behind this are simply that each instant is just as likely as every other instant to have an arrival, an arrow. The instants are independent of each other, and there's some long-run stable rate at which these arrows arrive. And if you make those assumptions, then there's no choice, you have to get this. So this was the exponential distribution. In other words, 1 minus that is a distribution function of the inter-arrival times. That's what's called exponential, and this has been one of the main models that we use throughout the course. So that means that if I'm going to use this, I should take the inter-arrival times to be exponentially distributed with some parameter lambda. Now in the statement of the homework problem, it says this. It says, assume that the inter-arrival times are exponentially distributed with mean value 5/8. That is, Poisson arrivals with rate lambda equals 1.6. So in other words, for the sake of our example, we're going to take lambda is equal to 1.6 arrivals per whatever. Let's call it per second. Which means that 1 over lambda, which is the average time between arrivals, is 1 over 1.6, or in other words, is 5/8 seconds. So in our diagram here, these arrivals are occurring, and the average time between them is 5/8 of a second. And that gives us 1.6 arrivals per second. So I'm just making these numbers up because they're nice numbers. So what would be the instruction here? Well, it would be exponential. So it's minus the average, which is minus 5/8, times the log of 1 minus a random number. So if I write this in here, this is going to generate arrivals occurring at random according to a Poisson process with a rate of 1.6 messages per second arriving at the channel. Okay, so that takes care of this guy. Minus 5/8 times log (1 minus RND). And in the statement of the problem, I'm going to run it in every case with this arrival process. And the point of the homework is to compare the performance for a single arrival process with different service time distributions. Okay. So then we go to instruction number 160. Let's see, I think I can erase this right here. So not 160, 170. So 170 asks you to define the numbers on the tickets that correspond to the service requirements. And there are going to be 3 cases. So here are the 3 cases. Case number 1, I'll take the service times to be exponential. So x is going to be exponential with parameter 2. So I'm just picking this out at random. I'm saying, okay, x is exponential with parameter 2. Lambda is equal to 2. That means that I write the instruction that generates what are called exponential service times. And the reason I'm using exponential, I mean, I could pick anything I wanted, but it turns out that exponential is important, not only because of the Poisson process, but it's important for another reason, which is that it's actually, believe it or not, the simplest assumption you can make and the one for which most formulas exist. So by using the exponential, we can compare with theory. If I use something else, then in some cases I can't compare with theory. Because one of the interesting things about this subject is that, as I say, it's on the boundary of an academic subject and what's really used. And so in this subject, some of the questions can be answered with formulas and some can't. And so that means that you have to use both simulation and theory back and forth in order to actually apply this stuff. So anyhow, if I assume exponential service times, then it turns out that there's interesting, easy formulas. The second case I want to consider is constant. And I'll take the constant equal to 1/2. So now, in this case, the bandwidth requirements of the messages are random. In this case, every message requires 1/2 a second in order to be transmitted. And in the third case, I'll take x to be uniform, 0, 1. Simply because, well, that's a nice simple thing, and it's sort of in between this and this. And so in every case, you see what I've done is I've chosen these so that the expected value of the service requirement is 1/2 second. So that means that I have to run this 3 times, and the instructions are going to be this. X equals, because I'm writing everything for you here. But that's because I don't want you to get bogged down in the technical details. I want you to see what's going on. So in case number 1, it would be minus 0.5 times the log of 1 minus a random number. In case number 2, it's 0.5. In case number 3, it's RMD. And you already know these because we've already done these before. So here I'm looking at a case in which I have a single Poisson process for the input in which the arrivals occur at a rate of 1.6 arrivals per second. And in every case, the average length of time that the server is busy with a message is 1/2 a second. And so the question is, well, if they all have the same average service requirement and they all have exactly the same input process, then what is the effect on the measures, namely the utilization of the server, the fraction of weight in the queue, and the average waiting time? Does it depend on either? Am I going to get different answers for different assumptions or not? Okay, that's the question. So we can answer that through theory, and then of course the simulation will show the theory's right. Okay, so where I stand now is, I think I've told you what you have to do for the simulation. Except for one last part. There's one curve you have to draw, but we'll get to that and that's easy. So any questions about this at the moment?
IA, we had a change the same with X, right? First,
IA is inter-arrival time. So in the simulation, I have 2 right here. I've got 2 stochastic aspects. This is where the randomness comes into play. If it weren't for this, if I didn't have randomness in the times between arrivals and the service requirement, then this would not be a probability problem. It would simply be one of, I don't know what it would be, just be descriptive. And as a description of reality, it would be worthless because you can't imagine a system in which you have messages that all have the same predictable arrival times and predictable service requirements. So I need to generate, in the simulation, to compare with the theory, I need to generate the arrival process, and I do that here by specifying inter-arrival times. I need to generate the service requirement. And the way I'm setting this up as an example to illustrate the main points here is I'm taking the inter-arrival times to be exponentially distributed, which means that I have a Poisson process for the arrivals, and we argued earlier in the course that that's the best description of total randomness, and the only parameter in there is the rate at which the arrivals occur. And I chose the rate to be 1.6 arrivals per second. So if you do that, then this instruction, every time I get to 110 and generate a new arrival, I'm sampling from this urn, or in other words, I'm generating the value from this formula. And this is the same formula that we've used before, so there's nothing new here in, nothing new here in sampling from these 2 random populations. Now, what I want to do is I want to compare, for the sake of this example, I want to compare the performance of the system in which I have a single arrival process, a Poisson process with a rate of 1.6 arrivals per second. I want to see to what extent the variability of the service times is going to affect the performance measures. So what I did was I picked 3 different populations or service time distributions, one exponential, one constant, one uniform, and they all have the same average value. So in every case, even though the individual values drawn from this urn are different, in every case, they average out to 1/2 a second. So on average, each message requires the server to be busy for 1/2 a second. And during that time, of course, anybody who arrives cannot use the server. So now to generate those values, you do it 3 times because I want to compare what's the difference between exponential service times with an average of 1/2, constant service times in which every service requirement is 1/2, or uniformly distributed service times which all vary between 0 and 1 and average out to 1/2. So they all have the same load on the server, but they all have different amounts of variability because they have different variances. And the question is, will the variability in the service time affect these different performance measures? And if so, how? And there are 3 performance measures we're worried about. The fraction of time the server is busy, or the utilization of the server, the fraction of customers who have to wait in the queue, the average time the customers wait in the queue. Okay? All right, so now you could do that, but if you ran it as is, all you get out is numbers, and so the question is, we want to try and understand this, because the purpose of all of this is insight and understanding, not just computation of numbers. So let me start on the queuing theory. Everybody okay on this? Okay. Okay, so now, when you go to the homework, it says, theory for the MG1 queue. And now what it does is it simply tells you some formulas, which I'm going to write down now, and I'm not going to derive these. That's actually done in the queuing theory course, but it's not difficult. And I say if you go to my website and look at the publications, don't look at the publications except for the one that's the encyclopedia article, because everything else will look much too complicated, because remember, it's research, it's not just applications, and that'll scare everybody away, and that's not the point. The point of putting the publications up there is to impress other people, but not to scare away students. So it's a trade-off there, like everything else in life. Okay, so now let me do queuing theory. I'm not going to have time to finish this, but I'll do this next time. But right now, you have enough information to run the simulation. Now, there's one other thing that I think is self-explanatory when you see it, which says that you have to change the code slightly because I want you to calculate not only average values, but I want you to calculate distributional values. In other words, the fraction of waiting times that are less than or equal to t for various values of t. There's a table, and you just run it and fill that in. So you could do that now, but it takes a minute. But before you do that, I want to get into the theory here. So the first thing is, it says that we have something in theory for the utilization. In other words, I'm going to predict what the utilization will be. And the mathematical symbol is rho, Greek R, and it's given by this formula. It's given by arrival rate times average service time if that value is less than 1. And it's given by 1 otherwise. So what this thing says is that the utilization of the server will be given by this formula. And what is that formula? Well, in our case, rho is equal to, lambda we said was what, 1.6? Lambda was the arrival rate. 1.6 messages per second. And E of x was the average service time, which was 1/2 a second. So that's equal to 0.8, which is less than 1. So in other words, that's the utilization of the server. In other words, 80%. So according to this theory, when I run this thing, this value over here, the sum of all the service times divided by the total time that the server was in operation, that is the total time the system was in operation, will turn out to be very close to 80%. The server is busy 80% of the time, it's idle 20% of the time. Now there's something that's rather remarkable about this. First of all, it's very simple. But second of all, can anybody make an observation about this? This observation is strange because if you didn't know anything about probability theory, you wouldn't make this observation. But if you do know something about probability theory, then it's strange that this is a true statement. Remember, if you don't know anything about probability theory, you always reason in terms of averages. Now, in this case, all the messages, all the three cases have the same average, but they have different amounts of variability. But this thing says that every case is going to give me the same answer. It doesn't matter whether I'm selecting from the exponential distribution, which is highly variable, or from the constant distribution, which is not variable at all, or the uniform distribution, which is in the middle. I always get the same answer. So in other words, the utilization of the server is insensitive to the variability of the service requirements. So if you know nothing, this isn't surprising because you wouldn't even know that there was another possibility. But if you know something, this is a surprising result. This is kind of strange about probability, which is that if you know a little bit, you're in trouble, right? If you know nothing, you're okay. If you know a lot, you're okay. But if you're in the middle, that's when you make mistakes. Anyhow, this is an observation. The theory says that you'll get the same answer in every case, and when you run the simulation, you'll see that you do. Okay, what about the second piece? It asks for the probability or fraction of customers who have to wait. And now it turns out that the answer to this question is this. So this is one of these things. I'll try and explain why later because I only got a minute left next time. This is also an amazing fact. First of all, it's easy to calculate. What this says is that the fraction or the probability that you have to wait in the queue is exactly equal to the fraction of time the server is busy. So if the server is busy 80% of the time, then 80% of the customers will have to wait in the queue. Now, the simulation will show that, but they're measured completely differently because the utilization is the sum of the service times divided by total time. It's a ratio of times. The fraction of customers who wait in the queue is the number of customers who have to wait divided by the number of customers who arrive. It's a ratio of integers. So there's no reason why those should give you the same answer. And in fact, they don't give you the same answer except in theory. In practice, they'll be slightly different because it's random. But when you run the simulation, you'll see that this value, and this value turn out to be the same thing. However, that doesn't always work. It works if the arrival process is a Poisson process. If not a Poisson process, this will not be a true statement. So this is surprising also. Now, it's hard to digest all of these things in one shot. And as I say, I'm going to get back to this. But let me say, write down the last formula. And here's the formula. I'll explain why this is or what this means next time, but I want to make out one point. The average waiting time depends on the variance. And so in each case, we're going to have different answers for the average waiting time, but we're going to have the same answer for the fraction of time the server is busy and the fraction of customers who wait in the queue. But if you think about it, this is truly astounding, because what it says is that the likelihood that you wait on the queue does not depend on how variable the service times are, but how long you wait on the queue depends critically on how variable the service times are. And the simulation will show that. So I'll start here next time. I'll discuss this and explain in more detail what this means. And when you run the simulation, you'll see that everything I say is true.